I'd like to discuss the following problem. So, a ball rolling down a ramp. So we have a ball of mass m 6 kilograms with radius r that rolls smoothly from rest down a ramp at an angle of 30 degrees. A question that we can ask about this problem is, if the ball descends a height of 1.2 meters during its motion, what is the speed of the ball at the bottom of the ramp? Here is a sketch of the problem. We have the incline or the ramp at 30 degrees from the horizontal. The ball starts from 1.2 meters above the ground level, and it's going to roll smoothly without slipping down the ramp. And the question is, when the ball is at the bottom of the ramp, what's the velocity with which the ball is moving? So essentially, what is the velocity of the center of mass of the ball? This is a problem that can be solved by using conservation of energy principles. The mechanical energy of the ball is conserved through the entire motion of the ball, since there are no external forces that act on the ball that dissipate energy. The initial position of the ball is at the top of the incline, and let's see what the mechanical energy of the ball looks like there. The initial mechanical energy is the sum of initial kinetic energy and the initial gravitational potential energy. Since the ball starts from rest, the initial kinetic energy is 0. And so therefore, at the initial position, the ball only has gravitational potential energy, which is mgh. At the final position, at the base of the ramp, the final mechanical energy of the ball is the sum of final kinetic energy and final gravitational potential energy. However, at the base of the ramp, the gravitational potential energy of the ball is 0. And so what we're left with is kinetic potential energy. Here we have rolling, so therefore we have two terms to the kinetic energy of the ball. We have a rotational term, which is 1/2 the moment of inertia of the center of mass I,, times the angular velocity of rotation squared, plus linear term, which is 1/2 mv,, squared. Applying the conservation of mechanical energy principle to this problem brings us to the fact that the initial mechanical energy of the ball is equal to the final mechanical energy of the ball. Or in other words, mgh is equal to 1/2 I, omega squared plus 1/2 mv, squared. Now the question is, what is the moment of inertia for the sphere? And I can look it up in the table in chapter 9, and that value is 2/5 mr squared. So I will substitute that value on the right hand side of this relationship here for I,. One more thing that I need to also consider is, since I'm looking for the velocity of center of mass, I also must express the angular velocity in terms of the velocity of center of mass. So the angular velocity is equal to v,, divided by r. Putting everything together, on the left-hand side I get mgh, that's the gravitational potential energy term. On the left-hand side I get 1/2 times 2/5 mr squared times v,, squared divided by r squared, plus the linear kinetic energy term, 1/2 mv,, squared. So here the radius squared is going to cancel out, and the 2's will cancel out as well. And now what we have is mgh is equal to mv,, squared over 5 plus mv,, squared divided by 2. I can also cancel the masses. And finally, I get that gh is equal to 7/10 v,, squared. So from here I can now express v,, and that is a square root of 7/10 times gh. And now I will substitute the numbers under square root and see what the final result is. So the final result for the velocity of center of mass is 4.10 meters per second. If the bow is sliding down the ramp, let's say it doesn't roll, it just slides, then the result for the velocity of center of mass will look different. From conservation of energy, I simply have that the gravitational potential energy at the top of the ramp is equal to the kinetic energy at the bottom of the ramp. And from here, the velocity of center of mass is simply equal to square root of 2 times gh. And so the velocity of center of mass in this case is equal to 4.8 meters per second. Notice that this is a different value compared to the case when the bow is rolling smoothly down the ramp. The reason for the difference is that part of the initial gravitational potential energy goes towards the rotational motion of the bow, or in other words, towards the increase of the rotational kinetic energy of the bow. Now let's answer a different question, and that is, what is the magnitude and direction of the frictional force that acts on the bow? In class we discussed that situation where the sphere or bow is rolling down the incline, and what forces are present in this example. So we have the normal force perpendicular to the incline. It's balanced by the y component of the weight of the ball. And then we have the x component of the weight opposed by the static friction force. Combined together produce the net force that causes the bow to move with acceleration x. I have enough information to calculate the value for x, and once I know the value, I can use it to calculate the friction force. The general expression for x that we got in the lecture is minus g sine of theta divided by 1 plus I divided by mr squared. So here I can calculate the acceleration of the center of mass for any object that is rolling down the incline, provided that I know the angle of the incline and I know also the moment of inertia of that object about an axis to the center of its mass. For a sphere, the moment of inertia is equal to 2/5 mr squared. And so then the expression for the acceleration of the center of mass becomes minus g sine of theta plus 2/5 mr squared divided by mr squared. So mr squared here and here will cancel out. Finally, the acceleration of the center of mass is minus 5/7 g sine of theta, which comes to be minus 5/7 times 9.8 meters per second squared times sine of 30 degrees. And from here I get that x is equal to negative 3.5 meters per second squared. To find the force of friction, I'm going to use the torque that the force of friction produces, and I'm going to make it equal to the moment of inertia of the ball times the angular acceleration of rotation of the ball. So Fs times r is equal to I times alpha. So from here, Fs is equal to I alpha divided by r, replacing alpha with its equal in terms of the acceleration of the center of mass and the radius. I get minus I times x divided by r squared. So the minus here, one more time, comes from the fact that the acceleration of the center of mass is down the incline, which is opposite to my choice of positive x orientation. Substituting I with the value for sphere, which is 2/5 mr squared, and canceling r squared in the numerator and denominator, I get the final expression for the force of friction. Minus 2/5 m x. Now I can substitute the values for the mass and for the acceleration of the center of mass to find the force of friction. And the force of friction, the force of static friction, comes to be equal to 8.4 newtons. Notice that in the final expression for the force of static friction, right here, there is no dependence on the radius. So no R dependence of the force of static friction. What does that mean? It means that it doesn't matter what the radius of the rolling sphere is, as long as the mass is 6 kilograms and the angle of the incline is 30 degrees, I'm going to get the same value for the force of static friction. So the size here is irrelevant as long as the mass and the angle of the incline are kept the same. And this is not a very intuitive thing to understand by simply looking at two objects with different sizes. But if they have the same mass, then that is the result.